Let's practice using the chain rule some more. And let's have some fun.
You ready to have some fun? Let's do it.
Let's compute the derivative of the function e raised to the power e to the x. It looks kind of strange, but the key thing to remember is that e to the x up there, that's in the exponent of the first e. So that's going to be the inside function when we apply the chain rule. I'm going to use Newton's notation on this one. That's going to be our g of x. Okay? What are we doing to that inside function? We're raising e to that power. So that's the outside function. We'll use f as the name for that function. If the input variable is u, corresponding to the inside function, then that'll be f of u equals e to the u. So the inside function is e to the x, the outside function is e to the u. They look like the same function. I mean, they are, but it's important to keep track of the difference in those variables. Okay, well, let's apply the chain rule. In this case, that says p of x, which is precisely the composition of f and g. Its derivative is given by the derivative of the outside function evaluated at the inside function, not the derivative of the inside function, but just evaluated at that inside function, times and g prime of x. Okay, now, here we go. We know the derivative of the exponential function, so I don't think there's any need to compute these derivatives separately from inside of this calculation. So that f prime, that's just again e to the whatever its input is. So let's do this in a two-step process. That f prime of g of x, that's just e to the g of x. And then we're multiplying by the derivative of g. Well, that would just be e to the x itself, because e to the x is its own derivative. And so finally, replacing g of x in that formula by what it is, which is e to the x, we get e to the x times e to the x. Okay, so that's one way of writing the derivative. If we want to use exponent rules here, since these have the same base, we could write this as e to the x plus x. Kind of cute. I like writing it that way.
Just a little, though. Don't overdo. Don't overdo. It gets working and it feels good, and next thing you know, you've overdone it.
Next example, let's take the derivative of f of x, which is 3 times the square root of x cubed minus 1/2 times the square root of x squared minus 5 times the square root of x plus 4. Now this is a really strange looking function. We wouldn't really come across this in nature, but I've written it in this way because I want to emphasize how this square root of x term is popping up 3 different times. That's going to be the inside function for the chain rule in this case. Alright, so each copy of the square root of x, each single copy on its own, is the inside function. That can happen. You can have the inside function occurring multiple times. The inside function is going to be the square root of x. I'm going to use the u notation again. Alright, what would the outside function be? Well, it would be the whole thing, but everywhere we see a square root of x, we're just going to think of it in terms of the variable u. So the outside function here is going to be 3u cubed. Remember, u is just shorthand for the square root of x here, minus 1/2 u squared minus 5u plus 4. So it might not have been so obvious that this was a composition, but it is in fact the composition of these two functions. It's first the square root function, that's the inside function, and then this polynomial. Now let's apply the chain rule. The derivative of f is Remember, it's the derivative of the outside function evaluated at the inside function times the derivative of the inside function. So let's first take the derivative of the outside function, but just with respect to u. Right? This is some polynomial, so we can take the derivative just by applying the power rule to each piece. So I bring that 3 down, and then I lower the exponent by 1. That's the power rule. I have minus 1/2. The constant comes along for the ride. I take the 2 down, and then I lower the exponent by 1. So that would just be u to the 1. That's just u. And then I have a minus 5, and the derivative of u is just 1. So in other words, the derivative of minus 5u is just minus 5. And 4 is constant. Its derivative is 0. So that right there, that is the derivative of the outside function. Let me notate that. It's the derivative of the outside function. All right. So in other words, if we're thinking of y as the total output of this polynomial, in other words, if I set this equal to y up there, then we can think of that derivative as the dy by du term in the chain rule, if we want to think of it using Leibniz notation. Now we need to multiply by the derivative of the inside. What's the derivative of the inside? It's the derivative of the square root of x. Do you have this one memorized yet? It's okay if you don't. The key is that to take the derivative of a square root function, let's see, we're taking the derivative of u with respect to x. Let me not write that as a u, let me just write it as the square root of x. But the key is to write that as x to the 1/2. So what's going on? I'm taking the derivative of the inside function, and I'm going to use the power rule, and I do so by writing the square root as just raising x to the 1/2. So that's the derivative of the inside function. Always got to remember to multiply by that derivative of the inside function. Now we're not done yet, right? The chain rule doesn't just say it's the derivative of the outside times the derivative of the inside. What's key is that you have to evaluate that derivative of the outside at the inside. In other words, you have to sub back in for u. That, since I wrote dy over du here, let me also include the du by dx notation for this piece, since that's what it is. Derivative of u with respect to x. Okay, and then what did I just say? We now need to evaluate this at the inside function. We need to plug the inside function in. So in other words, we need to sub in the square root of x for u. Here we go. So continuing the calculation, what do we get? Okay. Got to keep these parentheses. Everything's being multiplied. I have 3 times 3. Well, that's 9. And then instead of u, it's supposed to be the square root of x, right? So we have the square root of x squared. All right. Well, I guess the 2 was part of the outside function. I'm supposed to use blue for that. All right, I'm plugging in the square root of x for u. Here we have 1/2 and 2. Those cancel, right? 2 over 2, that's just 1. So then we have minus u. What's u? It's just the square root of x. And then the final piece is minus 5. There's nothing to plug in for there. It's just a constant. And now we're going to multiply by the derivative of the inside function, the derivative of x to the 1/2. How do we do that? We use the power rule. Bring the exponent down, subtract 1 from the exponent. That term is the derivative of the inside function. So now everything is present, and it's in terms of x. There's no more subbing in, plugging in that we need to do. So we can just evaluate. And we can make this look a little bit nicer. Check it out. The square root of x squared, that's just x by definition. And I see over here I'm going to have an x to the minus 1/2. There's going to be a big old fraction when I multiply. So I can write this as 9x minus the square root of x minus 5. That's that first part. But then multiplying by 1/2 x to the minus 1/2, that's the same thing as dividing by 2 times, the minus means we're in the denominator, x to the 1/2. In other words, 2 root x. So that's the derivative. That's one way to write it. All right, if we wanted to, we can simplify a bit. We can think of this as a sum of 3 different fractions. We'll have 9 over 2, and we'll have x over the square root of x. There's 2 copies of the square root of x in there inside of the x, so if we cancel them, I can write that as 9 over 2 root x. That middle term, once we split it apart as its own fraction, the square root of x's will just cancel, so we'll have minus 1/2. And the final term will be minus 5 over 2 root x. So you can also write the derivative that way if you want. I don't really see how one is better than the other. I don't know. Maybe the big fraction's sort of annoying. Maybe that's slightly better, but either is fine. Those are both good. But actually, this is an interesting problem. We're practicing the chain rule, so I used the chain rule to compute the derivative of this, but we didn't actually need to use the chain rule. So just as a reality check, let's compute the derivative a different way. All right? Just to check that we get the same answer. In other words, what I'm going to do now is compute the derivative of this function f. What was it? It was 3 times the square root of x cubed minus 1/2 times the square root of x squared minus 5 times the square root of x plus 4. All right, we're going to compute the derivative of that, not using the chain rule, but just using ordinary methods. In order to do that, I have to rewrite it. Right? It looks kind of funny. You can simplify this, right? What's the square root of x? That's x to the 1/2. Well, if I take x to the 1/2 to the 3, that's the same thing as multiplying those 2 exponents together. I can think of that as 3 times x to the 3/2. Here, the next piece, square root of x squared, that's just x by definition. And then the square root of x is x to the 1/2. And the plus 4 stays the same. So that's another way to write this function. And now if you write it that way, you can see, oh, we didn't need the chain rule. We could just compute the derivative of this function using just the power rule for each piece instead of the chain rule. Why am I doing that? I guess I'm a glutton for punishment? No. I want to just check that what we got before, this answer using the chain rule, is the same, right? It should work out the same both ways. This is a good, just a good test of our methods. Make sure we're doing everything correctly. All right, let's do it. Let's compute the derivative using the power rule. We bring the 3/2 down, and then we subtract 1 from the exponent. That leaves x to the 1/2. Next up, we have minus 1/2 x. That's just a single factor of x. It's a linear function, so the derivative is just that constant minus 1/2 up front. Okay, next piece. Again, power rule. We bring the 1/2 down, and then we subtract 1 from the exponent, like so. And then the derivative of 4, because we're adding 4, not multiplying, it's just a constant. The derivative of that piece is just 0. So there we have it. That's the derivative using the power rule instead of the chain rule. Is that the same thing as what we got up here? In fact, it is. It is. Check it out. I can rewrite this function, multiplying the constants together first of all, and then rewriting x to the 1/2 as the square root of x. Indeed, the first part's the same. The minus 1/2 checks out. That's just what it is. And then over here we have minus 5 over 2. And then raising x to a negative power means it's in the denominator. It's downstairs. X to the 1/2 means the square root of x. That's exactly what we got using the chain rule. It's the exact same thing. We got the same answer. Very, very nice. That's a good reality check. So if you can compute a derivative in 2 different ways, just to make sure you're doing your calculations correctly, it's a good idea to do that. Good idea to see that you get the same thing. So that's nice in this example.
But I wanna get you to try being creative on canvas. Just to take your time and sit down, have nothing in mind when you start. Just have a good feeling and be happy and in love with life and your world, and sit down and begin playing. And if you feel good about yourself and the world, it'll show in your painting, and all these little things will happen.
Okay, next up we're going to take the derivative of the square root of x times cotangent cubed of the square root of x. Looks real funky. Now we know that if we're taking a trig function to some power, right, that's cotangent of this raised to the third power, that's a composition. In fact, this is a threefold composition. First there's square root, then there's cotangent, then there's taking it to the third power. However, that's all separate from this other square root of x out front. Okay, that square root of x out front, that's being multiplied. So the first thing that we need to do here is the product rule before we do the chain rule. Let me write down how that's going to work. We're going to be looking at the derivative of that first function, square root of x, times cotangent cubed of the square root of x, plus the square root of x times the derivative of cotangent cubed of the square root of x, like so. Very good. So that first step was the product rule. Okay. Now here we have the derivative of the square root of x. We've been through this a few times now. The idea is to write the square root of x using x to the 1/2. It's still good to see all the steps, so I'm going to show you step by step. Meanwhile, over here in the other term, I'm going to start analyzing the derivative of cotangent cubed. Okay, this is a threefold composite, so I'm going to do this not using colors, but working my way outside in. The last thing that happens here is that we take cotangent of the square root of x and we cube it. So we need to take the derivative of that outer process, the cubing function. And then we'll evaluate at the inner function, which in this case is cotangent of the square root of x. So there's the power rule for cotangent cubed. And then we need to multiply by the derivative of the inside function. In this case, that'll be cotangent of square root of x. That was the thing that just got cubed. So just to recap here, what's this piece? This is the derivative of u cubed, where u is that inner function, cotangent of square root of x. That's the derivative of the outside in the chain rule. And then this is the derivative of the inside function. So that's one application of the chain rule. In the next step, we're going to need to analyze this derivative again using the chain rule. Okay, back to the beginning of the expression. What's the derivative of x to the 1/2? We use the power rule. Bring that 1/2 down, subtract 1. Cotangent cubed square root of x doesn't change, that's just going to come along for the ride. Alrighty. Next up, everything here isn't going to change. I guess I could have moved that 3 out front. Notice that it's not inside the square root symbol. I'm going to write cotangent squared in the more traditional way, writing cotangent squared of square root of x. That kind of cleans up that expression. And now it's time to take the derivative of cotangent of square root of x. That's another instance of the chain rule. First off, we need to take the derivative of cotangent of the inner function. What's the derivative of cotangent? It's minus cosecant squared of that inside function. And then we need to multiply by the derivative of the inside. That's one more application of the chain rule. So here, what's this piece? That's the derivative of the outer function, which is cotangent of u, where in this application of the chain rule, u would be the square root of x. On the other hand, that's the derivative of the inside function. Derivative of just u itself. So we've applied the chain rule twice in those last two steps. Very nice. Alrighty, we're almost done. Just need to let the pieces all fall together. Let's simplify a bit. Out front we'll have 1 over 2 square root of x times cotangent cubed of the square root of x. Now let's move this minus sign out front, and let's move that 3. I like to put the constants out front. So the minus sign and the 3 come out. We're left with square root of x cotangent squared of the square root of x. And then what's left in here? We have a cosecant squared of the square root of x. And then finally the derivative of the square root of x. We've taken that a few times now. In fact, we just took it over here. We know it's 1 over 2 root x. So I'll just sub that in. And now we're done. That's it. That's the derivative. We took the derivative twice in analyzing the derivative of cotangent cubed of the square root of x. It's a threefold composition. We had to use the chain rule twice. I feel like there's some common factors, so I think it's worth writing this a little bit in a more nicer way. Let's see, what are the common factors? Well, there's a 1 over 2 root x that's being multiplied by both of these terms that we're subtracting. And now there's cotangent of the square root of x, and there's 2 copies of it, right? Factoring those common terms out, we can write the answer this way as cotangent squared of the square root of x divided by 2 root x, all times cotangent of the square root of x minus 3 root x cosecant squared root x. My oh my. Another way to write it would be to cancel the square root of x's here and here, bottom and top. So I could have also written it as just this term minus 3 cotangent squared square root of x cosecant squared square root of x. I don't know. Sometimes it's not clear what the best way to write the answer is. Regardless, there's the derivative.
It's a good day to be alive. Come to think of it, every day's a good day to be alive.